So we looked at some of these examples last time. We talked a little bit extensively about CP. Fields are just community frames of identity where all the non-zero elements are in fact units. They're invertible, integral domain. Not quite as strong as a field. Oh, such that there are no non-zero or no non-zero zero fractions. So in other words, you get that little dream come true. The product of two things being zero means one of the two things is zero. So, of course, any field is an integral domain, right? Right. Let me prove that for you really quick. Suppose that A times B equals zero. Well, suppose we're living in a field, and suppose that you have the equation A times B equals zero. And well, if A is zero, then you're done. If it's not zero, then multiply by A inverse. So AB equals zero means that one of the two has to be zero. So any field is an integral domain. The converse is not true. Can anybody give an example of an integral domain? So that is a commutative ring of one, and it's got no zero divisors up to zero, but it's not a field. Anybody got any examples? What's the first commutative ring with identity that you can think of? What's kind of a good prototype example of commutative ring with identity? How about this? The only zero divisor in Z is zero, right? Because if you have two integers m and m times n equals zero, one of those has to be zero. Agree? It is not a field. Because, for example, 2 is not a unit, because 1/2, its multiplicative inverse is not an integer itself. Everybody okay? Here is a theorem that you might be able to piece together. In general, integral domains are more general than fields. There are many integral domains that are not fields. But if it's finite, the notions are equivalent. Can somebody tell me why this is true in Z mod n? What do you know in Z mod n? What do you know about any element of Z mod n? Very good. It's either a zero divisor or it's a unit. Agreed? And so let's suppose you have a finite integral domain. That means there aren't any zero divisors other than zero. That means that every non-zero element must be a unit, right? So it's a field. Everybody okay with that? We will prove this in general. And the proof is very much the same. Let R be a finite integral domain. And A and R be non-zero. Non-zero. What do we have to do? The burden is now on us to show that A has an inverse. Everybody agree with that? We got to show it's a unit. We got to show it's got an inverse, right? So somehow the finiteness must creep in, right? Any ideas on the difference? One thing that you can do is you can look at powers of A, right? A squared, a cubed, a fourth, forever and ever, right? Notice that some power must repeat itself, right? Because of the fact that it's finite. Everybody okay with that? This is very similar to what we did in ZN. You can prove it that way. I'm going to prove this a different way. What I'm going to do is I'm going to do some counting. The function. So I input an element of the ring and it outputs A times X, right? Where A is this fixed element. So basically what this function does is it reads the input and multiplies by it. Everybody agree with that? Notice because this is a ring, your input is an element X, your output AX is an element of R as well. Agree? Number one, I claim F is 1 to 1. How do you prove something's 1 to 1? Remind me how we prove something's 1 to 1. That's how we prove something is 1 to 1. If f of x equals f of y, we need to conclude that x equals y. Everybody agree with that? So let's take a run at this, shall we? Suppose f of x equals f of y. So this means ax equals ay. And remember, we got to come to the conclusion that x equals y. What are you so tempted to do here? That's right, we'll cancel that, right? Got to be a little bit careful because I don't know if I've got vision. I will be a little bit careful. I'm going to write it this way. Sure enough. Now, what can I do? What's a natural thing to do here? Agreed. Yes.
When you say you don't know if you have division because it's a ring, multiply.
That's right. To have division, I have to multiply both sides by A inverse, right? A priori, I don't know that A has an inverse that lives in this ring. So I'm being super careful. So look at this equation right here. A is not 0, and A times this number is 0. So what does this mean about this number?
0.
That is right. This implies x minus y equals 0, as R is a integral domain. Everybody agree with that? Because there are no non-zero divisors. I know that A is not 0 because that's the way that I picked it. So that forces the hand of this other one to be 0. Agree? Everybody okay with it? So here's what we have. So f, the domain and range of this function f is R. Agreed? You have a one-to-one function from a finite set to itself. What do you also know about this function? The function must also be onto, right? Because these two have the same element. Maybe they got 10 elements, right? The domain has 10 elements in it, and everything goes to something different, so it's got to cover everything, right? Everybody agree with that? So because of the fact that R is a finite set, and this is one-to-one, since since no two elements go to the same thing, you've got to cover everything in R. Agreed? Note, one is in R, right? And F is onto. So there exists X and R such that X equals 1. Agree? Because one's an element of the ring and it has to be covered. And f of x is ax. So x is the inverse way. And R is.
And how do we know x is the inverse then, just because when they're multiplied they equal 1?
That's right, because A times X is 1.
Okay, and that is a property of the field?
Yes, what it means to be a field is every non-zero element must have an inverse,
Okay,
a multiplicative inverse.
and that inverse takes you back to 1.
That is correct.
Okay.
Right, okay with that? Notice, there's something interesting about this. I can't resist the remark here. This function here is one-to-one, right? And it also meant it was onto. That only works because R is finite. Notice that if you replace R with the integers, this proof no longer works. And it shouldn't work because there are elements of the integers that don't, in fact, most elements of the integers don't have a multiplicative inverse. And the problem is when you have infinite sets, you can have a one-to-one function that is not onto. For example, take the function from the integers to itself where you multiply everything by 2, right? That's certainly one-to-one, right? 2x equals 2y means that x equals y, but it's certainly not onto because no odd number is covered by that. Any questions on let me finish up with the definition that you already know, because we've already done this for ZN, but I'm gonna formalize it just by telling you what it is in general. Definition. The a ring and X an element of R. So I'm gonna put some descriptors on what we can call that. So number one, X is a unit of R if there exists Y in R such that X, Y is not. And of course, we had this for Zn where you find something X, Y equals 1 bar. 2, X is a zero divisor of R if there exists Y and R such that it's a zero divisor if there is a non-zero Y such that X, Y equals 0, and 3, X is nilpotent if X to the n is 0 or some n the natural numbers. Okay. Okay, I'm going to introduce something now. So we're going to talk about something called ideals and something called homomorphisms. One of the good things about this kind of mathematics is we already know what a homomorphism is for groups, right? It's essentially the same thing over and over again. These kind of ideas in mathematical structures are often used over and over again. It's usually kind of the same sort of way of looking at things. What is an ideal, right? This is a different word. Well, an ideal is analog, actually, ideals are to rings what normal subgroups are to groups, right? So subrings are to rings what subgroups are to groups, and ideals are studied, especially ideals are studied more than subrings actually in rings, and they're kind of important. So let me tell you what ideals are. Definition. And remember, unless I tell you otherwise, my rings are all commutative and have one. We're going to assume that. An ideal I in R is a subset of R such that two things, and there should be two things, because what is different about a ring as opposed to a group? Well, a ring's got two operations compared to the group's one. So the first thing I want is, remember, a ring, the first thing we say about a ring is it's an abelian group, and then it's got this multiplication. So if I want to talk about these substructures, it better be a subgroup, right? And that's all the first thing is here. Number one, I is a subgroup of R. And here, of course, what I mean additively. So it's just a subgroup under addition. And here's what sucks about an ideal, and it really does suck. Number two, xi, or I'm sorry, right, xi is contained in I for all. So another way to put this is, so let me put it in sort of an element way for you. And this is what I mean by it sucks. It truly does, because it's like a vacuum cleaner. It sucks everything from R into I. When you have something in I, when you have something in this ideal and something in X, you put them together and it sucks you right into the ideal I. So let me give you some examples. Always a good place to start to look for examples. Look at the even integers. This is a subgroup, right? Okay, so the first hurdle is over, right? This is certainly a subset. It's closed under addition and subtraction, and it's got the identity, right? And it sucks, doesn't it? Because if n is in the integers and 2k is in the ideal 2z, then n times 2k is 2. That is to say, when you multiply any integer times an even integer, what do you get? An even integer. So it sucks everything right on in there. Can anybody generalize my example here? Instead of just multiples of 2, what could I do? But what I am, all I mean by that is this is just all the multiples of m. All right. This is an ideal. And in fact, I think we proved earlier in one of the homework problems that we had earlier that this is in fact a subgroup. So we've got that, right? Because we proved in homework that any, if you have like any MZ, anything like this, it's actually a subgroup of Z. And it certainly sucks, doesn't it? Because if you multiply any integer times a multiple of m, what do you get? A bigger multiple of m, right? Can somebody explain why these are in fact the only ideals of Z? Once again, that homework might have been helpful. Y'all remember that homework? Part of that homework, the hard part of that homework was we showed in this homework that these were all subgroups of the integers, and then we used the Euclidean algorithm to show these were the only subgroups of the integers. Y'all remember that? These are the only subgroups, so they're the only ones that have a chance to be ideals, because ideals have to be subgroups. And they all work, so that's an exhaustive list. Notice you have a couple of extreme examples. When m equals 0, you get the ideal 0. So notice that's true. If you have any ring, the subset 0 is itself an ideal, right? Because it's certainly a subgroup. And it certainly sucks, because if you multiply anything by 0, it's 0, right? And the other extreme is the whole ring is an ideal. We say that an ideal is proper if it's not the whole ring, right? It's properly contained. Let me give you a non-example just for contrast. RBQ, right? And in fact, this is field, right? But it's certainly a community ring identity. Z is a subgroup. And let me emphasize again, I'm feeling addition. But it's not an ideal. And somebody quickly explain why is it that Q is not an ideal? It's certainly a subgroup. All you have to do is give me one example of why the sucking power, why the vacuum doesn't flow.
So I think that's a dumb question, but what are the rational numbers again?
They're just quotients of integers, 3 7s, 2, any quotient of integers. Can somebody name, so I claim that it's not an ideal, so it doesn't suck things in. Z doesn't suck things in very well. So what you need to do is find me an integer and a rational number such that their product is not an integer. If I do that?
Then just do it 1/2 times 1.
There you go. 1/2 is in Q, 1 is in Z, but 1/2 times 1. So this doesn't have the vacuum cleaner power that you need. This is a subgroup, but not an ideal.
Now, to be an ideal of Q, what like,
Okay, so now she wants to know what the ideals of Q. That's a great question. And in fact, there's only 2 of them. I want to give you a theorem. While you puzzle over that, I think I might be able to clear that up a little bit with the following theorem. That's a great question. So here's a theorem, kind of utilitarian, but I think it'll help with that question and others. Let's see, lemma something or other. 2. Suppose R is a ring with identity. I want to put the word 1 in here for emphasis. That's going to actually be important here. And I and R are an ideal. Now, as we've pointed out, the ring itself is an ideal, and it's extreme. That's as big as you can get. If and only if I contains a unit in R. And number 2, if R is commutative, you can assume commutative with identity for this, but I emphasize this because really this is all you need. You don't need commutative in the previous statement, really. If R is commutative, then R is a field. If and only if 0 is the only proper. And again, proper means the only ideal other than R itself. So anyway, I think this will address your question very well, because the ring you asked about was Q, which is a field, right? So if you believe this, Q is a field, that means that the only proper ideal is 0, right? Every other ideal is all of Q. Let's see why this is true. Let's prove number 1 first. Notice this is one of these pesky if and only ifs, and so it's that one. So we'll prove this direction first. Suppose I equals R. Since 1 is in R, 1 is in I. And there we go. Because remember, our burden is to show that I must contain a unit. Well, it contains 1, and 1's a unit. Everybody okay with that? That was the easy one, right? If I equals R, then there must be a unit in I. Here's the magic of the vacuum. How do we work it the other way? Suppose that I contains a unit. I claim that I is all of R. Okay. Well, let me deconstruct this first. Suppose U is a unit. What does this mean? So U inverse is in R, right? Now, let R be any element of R that I want. R is equal to everybody agree with that? Nothing up my sleeve. This thing is in R, and this thing is in I, right? Because U is an I. And what do ideals do? They suck, right? So when you multiply these two things here, it has to be in I. Everybody agree with it? So every R in R is in I. So R is equal to I. Because it's certainly true that I is contained in R. So now R is contained in I. Any questions? So first one down. The ideal is the whole ring if and only if it contains a unit. Okay, what about the second statement? The one that answered the earlier question. If R is commutative, then R is a field if and only if 0 is the only proper ideal. Okay. So R is a field. And suppose that R is a field and you have some ideal that is not zero. That means there's at least, of course, zero must be in every ideal because it has to be a separate. So what this statement here says is I must contain at least one thing that's not zero. Agreed? Now you can bootstrap off number one for this. By the way, what's the burden here? To get the result I want, I need to show that if I is not the zero ideal, it's not proper. That is, it's everything. Agreed? Since I is not the zero ideal, just pick any element out of it that's not zero. What do you know about alpha? When you think about that, don't get too far afield. Alpha is a non-zero element of I, so it's a non-zero element of R. And what is R? What are we assuming about R here? Right, but in the beginning of two, what are we? It's a field. So if you have a non-zero element alpha, what's true about it?
Unit.
It's a unit. Let's go back to one. Since R is a field, alpha is a unit. So I contains a unit. I is equal to R because it contains a unit. Right, proved it. Everybody okay with that? I is a non-zero ideal, contains a non-zero element. That non-zero element must be a unit, so I contains a unit, so it's everything. So basically what this shows is you've got two ideals, zero ideal and the whole thing. Let's do the other direction. Suppose this one's fun too. Now suppose zero is the only proper ideal of all. Now, what we're trying to do is show, what the heck are we trying to do? We're trying to show that R is a field, right? So you have to show that any non-zero element has an inverse, right? Or any non-zero element is a unit, right? So let alpha be a non-zero element of R. Now, I want to look. Here's a notation I want to introduce. This means the ideal generated by alpha. And what in the blazes do I mean by that? I just mean the set of all multiples of alpha. I claim alpha is an ideal. Of R. Okay, let me make a couple of observations. Notice that this thing contains zero because zero times alpha is zero. That's in there. And two, if R1 alpha and R2 alpha are in a multiple of alpha, then R1 alpha plus R2 alpha is R1 plus R2 alpha. It's also a multiple of alpha. Okay, so it's closed under addition. And three, if R2, or I'm sorry, R alpha is in alpha, then minus R alpha in alpha. And so it's got inverses. So I've proved everything that I need for subgroup except for associativity of addition. And I don't need that because it's already a ring, so I've already got associativity of addition. So it's a subgroup. Everybody okay with that? And it's a vacuum cleaner. Does vacuum have one or two C's? I don't know either. It sucks.
Take two.
How many?
Two.
Does it? Yeah.
Yeah, it doesn't look
I don't
good.
know. That looks worse. Well, let's just call it three. So if you look at R, then T, R alpha. So this is an ideal, right? So we're just about to finish up. I proved that that's an ideal. So it's an ideal and it's got alpha in it, and alpha is a non-zero element. And so what was my assumption here? I suppose we were supposing that zero is the only proper ideal. So since this is a non-zero ideal, that ideal must be the whole ring, right? Because it can't be proper. Everybody okay with that? So since one is in R, and R is the ideal generated by alpha, then there exists R in R such that R alpha equals 1. So alpha. And there you go. Any questions? Now, perhaps more in group theory, we like to add descriptors to our ideals because certain ideals have different flavors that are very useful. Any questions on this proof? I want to tell you about certain kinds of ideals and give you some examples. First, I'm going to go through kind of a list of definitions. There are many, many descriptors for ideals. I'm going to focus really on three of them here. So I'm going to go through these definitions before all at once I'll come to this. Definition 724. An ideal, let me emphasize this, a proper ideal. Is maximal what do you suppose it means to be a maximal ideal? It just means it's as big as possible, right?
As is contained in R, or is that notation?
This means it's contained in R, but not equal to R.
Okay,
That's we double emphasizing the property. If it is as big as possible. Now that's really imprecise, so let me give you something that is precise. What it means to be maximal is you can't squeeze another ideal in between M and R. If you try to squeeze something between N and R, you're forced to either be M itself or R. So maximal just means as big as possible. There's a more the next one has a more general definition. I'm just going to give you the one that applies to us. Definition 7.2.5. Or commutative one. Proper ideal. Again, proper, strictly contained in R. It's said to be prime if A, B, and P implies A is in P or B is in P. Now, ideals suck stuff in, but what this says is something a little bit different. If you have two things that multiply together and you find that their product ends up in the ideal P, one of those things that multiply together has to be in there. And finally, I'm going to define something else called radical. And we'll talk about this, some examples, but I'll give you sort of just some thought homework to think about. See if you can come up with what the maximal ideals, the prime ideals, and when I'm done with this, the radical ideals, and the integers are. Definition. Again, R commutative one. And here, I guess ideal. We define the radical of I. I use this notation a lot, this square root sign with this. This is a set of X and R such that X to the N is in I. So, so the radical of I is a set of everything that some power of it ends up in the ideal I. We say I is radical if I is equal to its radical. So in other words, if when you take a power of something and you find it's an I, it's already an I. So my homework is think about the integers, see if you can figure out what the maximal ideals, prime ideals, and the radical ideals are. And they're all at least slightly different for the integers. Okay, any questions on that? Any questions? Okay, put that in your pipe and smoke it. See if you can wrap your head around some of these definitions, and we'll do some examples next time to kind of help you out.